In electrical engineering, we often encounter non-sinusoidal waveforms. The sawtooth wave is a fundamental signal where the voltage increases linearly and then drops instantly. Understanding its effective power requires us to calculate its root mean square value, or RMS. The RMS value represents the equivalent DC voltage that would deliver the same average power to a load. For a varying signal like a sawtooth, we cannot simply use the peak value, we must find the statistical average of the squared signal. The RMS calculation follows a three-step process indicated by its name. We square the function, find the mean over one period, and then take the square root. This formula allows us to quantify the effective magnitude of any periodic waveform. To solve for the RMS value, we first need a mathematical expression for the voltage. For a sawtooth wave starting at 0, the voltage is a linear function of time, defined by the peak voltage divided by the period, multiplied by time. Step 1 is to square the instantaneous voltage. Squaring the linear term t results in a quadratic term t squared. This transformation ensures that all values are positive, which is essential for calculating the total energy content over the cycle. Now we integrate this squared function over one full period. This step calculates the total's area under the squared voltage curve, which is the core component of finding the mean value of the signal's power-related profile. Applying the power rule for integration, the integral of t squared becomes t cubed divided by 3. When we evaluate this from 0 to t, the t squared in the denominator cancels out 2 of the t terms from the numerator, leaving us with this simplified expression. The final step is to take the square root of our mean value. The square root of v peak squared is simply v peak, and we are left with the square root of 3 in the denominator. This is the universal RMS formula for any sawtooth wave. Let's apply this to a real example. If we have a sawtooth wave with a peak of 173.2 volts, we divide by the square root of 3, which is approximately 1.732. The resulting effective voltage is exactly 100 volts RMS. It is helpful to compare this to a standard sine wave. While a sine wave's RMS is the peak divided by the square root of 2, the sawtooth uses the square root of 3. This means for the same peak voltage, a sawtooth delivers less power. When calculating average power, the RMS value is vital. By squaring the RMS value and dividing by resistance, we find that the average power of a sawtooth wave is exactly 1/3 of the power that a DC voltage of the same peak value would provide. Interestingly, as long as the waveform consists of linear ramps that return to 0, the symmetry of the rise and fall does not change the RMS value. Whether it is a ramp or a triangle, the factor of 1 over root 3 remains constant. Visually, you can remember that the RMS value of a sawtooth sits at approximately 57.7% of its peak. This is lower than the 70.7% level found in sine waves, reflecting the thinner shape of the sawtooth's profile. To summarize, start with the linear equation, square it, integrate over the period to find the mean, and take the square root. The result is always the peak voltage divided by the square root of 3, providing the effective DC equivalent. Let's test your understanding. If a sawtooth wave is measured at 10 volts RMS, what is its peak voltage? Use the relationship we just derived to find the answer. Remember, the peak must be higher than the RMS. The correct answer is 17.32 volts. By multiplying the RMS value of 10 by the square root of 3, we find the peak. Thank you for joining this lesson on waveform analysis. Generated by Vision Solve AI.